When you hold your smartphone, you're holding a device that processes billions of operations every single second. But inside that sleek glass sandwich, a physical traffic jam has been building for decades, threatening to stop Moore's Law in its tracks. For the last 50 years, we've built chips like a house where the plumbing and the electrical wiring are all forced through the front door. We call this front-side power delivery, and it's reaching a breaking point. As we shrink transistors down to the 2 nanometer and 1.6 nanometer scale, there simply isn't enough room left for both power and data to coexist on the top layers. The engineering behind how we solve this is absolutely brilliant. To understand the problem, you have to look at the BOL, the back end of line. This is the massive stack of metal layers sitting on top of the actual transistors, acting as the chip's nervous system and its power grid. In a traditional chip, the power has to fight its way down through 15 or more layers of metal just to reach the transistors at the bottom. By the time the electricity gets there, it's lost a significant amount of its energy. This is known as IR drop, a loss in voltage caused by the resistance of those tiny cramped wires. It's like trying to water a garden using a mile-long straw. You lose pressure every inch of the way. But it's not just about power loss. These power lines are bulky, and they take up precious space that could be used for data. It's a zero-sum game. Every wire used for power is a wire you can't use for information. This congestion creates routing bottlenecks. Designers have to take long, circuitous routes for data signals just to avoid the power grid, which slows down the entire chip and generates massive amounts of heat. To go faster, to go smaller, and to be more efficient, we had to rethink the very geometry of the semiconductor. And the solution TSMC found is as radical as it is simple. Flip the power upside down. Imagine a skyscraper where all the elevators and all the plumbing are in the same narrow shaft. It's a nightmare. Now imagine if you moved all the plumbing to the outside of the building. That's backside power delivery. By moving the entire power distribution network to the back of the silicon wafer, we decouple power from data. This isn't just a minor tweak, it's the biggest architectural shift in chip design in over a decade. TSMC calls their version the superpower rail, and it's the secret sauce behind their upcoming A16 node. It's how they plan to maintain their lead in the race for 1.6 nanometer supremacy. The engineering challenge here is staggering. You have to manufacture the transistors first, then flip the entire wafer over, thin it down to almost nothing, and then build a whole new metal network on the back. We're talking about thinning silicon down to a few hundred nanometers, thinner than a strand of spider silk, without breaking the delicate transistors already etched onto the other side. It sounds impossible, but the results are worth it. This shift unlocks performance gains that were previously thought to be years away. Let's look at exactly how they pull it off. The heart of this revolution is the through-silicon via, or TSV. These are microscopic vertical tunnels that act as the elevators for electricity, connecting the back of the wafer directly to the transistors. In the old way, electricity had to travel through a long, winding staircase of metal layers. With the super power rail, it's like having a dedicated express elevator that takes you straight to your floor. Because the path is so much shorter and the wires can be much thicker on the backside, the resistance drops dramatically. This nearly eliminates the IR drop we talked about earlier. But TSMC's A16 node takes it a step further. Instead of just general backside delivery, they're using nano TSVs that connect the power rail directly to the source and drain of the transistors. This precision allows for a massive reduction in standard cell size. When you don't have to leave room for power rails on the front, you can pack the transistors much closer together. We're looking at an area scaling improvement of about 10%. That might not sound like much, but in the world of semiconductors, a 10% density boost is the difference between a generational leap and a plateau. Now, let's talk about the data lines. With the power rails moved to the back, the front side metal layers are suddenly empty. This is like clearing all the trucks off a highway so the sports cars can race. Engineers can now use these freed-up layers to create more direct, lower latency paths for data signals. This reduces the RC delay, the time it takes for a signal to travel across the chip. The result is a chip that can clock higher and run faster without needing more power. TSMC expects the A16 node to provide an 8 to 10% speed gain at the same voltage compared to their 2 nanometer process. But how do you actually build this? It starts with a carrier wafer. You bond your active transistor wafer to this carrier face down using a special adhesive that can withstand extreme heat. Then comes the thinning. Using a process called chemical mechanical polishing, or CMP, the back of the device wafer is ground down until the silicon is almost gone, exposing the bottom of the transistors. Once the back is exposed, you use extreme ultraviolet lithography to etch the new power rails. It's like building a second mirror image chip on the bottom of the first one. This process is incredibly delicate. If the two wafers aren't aligned to within a few nanometers, the TSVs won't line up with the transistors, and the entire multi-billion-dollar batch is ruined. To solve this, TSMC uses advanced optical sensors and AI-driven alignment systems that can detect shifts smaller than the width of a single atom. The level of precision here is almost hard to wrap your head around. And here's the clever part. By putting the power on the back, they've also created a new way to manage heat. The power rails can now act as a massive heat sink, pulling thermal energy away from the transistors. The transition to the A16 node and the super power rail isn't just a technical milestone, it's a competitive necessity. TSMC's rivals like Intel with their PowerVia technology are racing toward the same goal. By moving to 1.6 nanometers, TSMC is entering the angstrom era, where we measure features in units smaller than a nanometer. At this scale, we are literally manipulating matter at the atomic level. The A16 node is expected to enter volume production in 2026. It will likely power the next generation of AI supercomputers and the smartphones we'll be carrying in just a few years. But the implications go far beyond just speed. Because the power delivery is so much more efficient, these chips will be able to do more work while consuming significantly less energy. For data centers that consume as much electricity as small cities, a 15 to 20% reduction in power usage is a massive deal. It's the difference between needing a new power plant and being able to scale with what you have. This efficiency is what will allow AI models to keep growing. As the demand for compute explodes, the super power rail provides the physical foundation to keep that growth sustainable. We are also seeing the beginning of true 3D integration. Once you've mastered building on both sides of a wafer, the next logical step is to stack multiple active layers on top of each other. This is known as CFET, or complementary FET. It's a future architecture where N-type and P-type transistors are stacked vertically, potentially doubling the density of chips once again. The super power rail is the enabling technology for this 3D future. You can't stack transistors if you're still trying to shove power through the front door. You need that backside access to make the whole system work. It's easy to take the chips in our pockets for granted. We see the apps, the games, and the AI, but we rarely see the incredible feats of mechanical engineering happening at the atomic scale. The superpower rail is a reminder that progress isn't just about better software, it's about solving the hard, physical problems of resistance, heat, and space. It's about the brilliance of engineers who looked at a 50-year-old design and decided to turn it completely upside down just to find a few more nanometers of room. Next time your phone does something that feels like magic, whether it's generating an image or translating a language in real time, remember the superpower rail. Remember that deep inside that device, electricity is taking an express elevator through a thinned-out silicon wafer, bypassing the traffic jams of the past to power the future. The engineering is invisible, but the impact is everywhere. We're not just shrinking chips anymore, we're reimagining what they can be from the inside out.